Okay, so today is the grand finale, where I show you a sketch of the proof of the Graph Minor Theorem that all the finite graphs are well quasi-ordered by the Graph Minor relation. I'll show you a sketch of a possible proof. The actual proof is a little different in many details, but I'll show you a proof that brings together the various threads that we have begun to weave into this pattern, and so you can see where everything has its place, and I hope that will be rewarding. So before we start, we need one more theorem, which I can only show you. That's complicated enough. I can only state it, but not prove it. And that is a structure theorem for the graphs that don't have a kn minor. So pick your favorite n, fix it, and then we can ask all the graphs that do not contain this particular complete graph on n vertices as a minor. Can we say anything about their structure? So like K5 and K33, if we exclude those, what can we say about the structure? Well, the graph will be planar if it doesn't contain them. Right? So it's a similar thing, and actually a planarity or slightly more generally embeddability and surfaces will feature. And the theorem is up there. So I wrote it out for you to see. And it says that for this arbitrary but now fixed n, there exists a k that rules the structure. And every graph that doesn't have kn as a minor has a certain tree decomposition. It has a tree decomposition whose torsos, remember, so when we have a tree decomposition, the torsos are the parts with adhesion sets made complete if they're not already complete. So those are torsos. And the torsos have to fit into a surface, or nearly fit into a surface. And what surface? Well, not any surface. Of course, every graph fits into some surface, but into a small surface, small enough that Kn itself doesn't embed in it. Right? So the main point is that there is a bounded number of surfaces, a bounded set of surfaces, into one of which every torso fits. So every torso can choose its own surface from those boundedly many surfaces. When I say boundedly many, that always means bounded by a function of n. Right? So, for example, something in terms of k is always going to be boundedly many. Right, so the torsos, not just the parts, but the torsos have to nearly fit into one of these boundedly many surfaces. Now I need to tell you what nearly fit means. And so let's look at one torso now. And we have a surface. And we want to fit the torso into this surface. And before we attempt to do that, we're allowed to delete from this torso up to k awkward vertices. So we don't have to even attempt to embed the entire torso, but if there are some really, really nasty surfaces, for example, nasty vertices, for example, vertices adjacent to everything else or something, we're allowed to delete them first, as long as we don't delete more than k. And then, once we've done that, so I'm here now, after deleting up to k vertices, and we'll call them apex vertices. well, the picture is that you have this torso here, and then there are a few nasty vertices included in the torso, which we imagine to sit at the top, and they are adjacent to lots and lots of stuff in the rest. So they're called apex because somehow they sort of stick out. After deleting at most k apex vertices, the rest has to fit not quite into the surface, but into the punctured surface. From this surface, we're allowed to delete up to k points, just pierce a hole in the surface. And once we've pierced a hole in the surface, we can sort of widen the hole a little bit. Like this, or phrased more mathematically, deleting a single point is topologically the same as deleting a closed disk. Right? And then in these boundedly many holes, we're allowed to embed something called vortices. So a vortex is something in the sea that whirls around and sucks you in, and you're big four-master, and you see lots of magnificent creatures on the way down into the abyss, and so that's a vortex. It's a long history in literature. So these vortices are terribly terrifying, whirly things like this. I'll give you a precise definition in a moment. So we have up to k of these additional little bits of graph that don't need to fit in the surface itself, but fit around the edge of a disk. And we have boundedly many such disks. So let me make this more precise. Well, that's too small still. So one such thing. So the surface is out here. And this is the hole that we've cut into it, the surface. Then we're allowed to hang some bags onto as many points in this hole as we like. So that's important. The number of these points that are going to be images of vertices of the graph we're embedding, or nearly embedding, is unbounded. There may be as many of those as we like. And then we hang on those pegs some boundedly large bags, so size bigger, less than k, which form a path decomposition, or nearly so. These graphs in here, the little graphs in there, they conform to the axioms for a tree decomposition if we delete one of them. So to delete one of them, then we have a long path here, an imagined path, along the rim of this hole. And these bags form a tree decomposition with the tree being this path. Okay, so whenever you have a vertex sitting in here and it's also at the same time sitting in there, then it must be in every bag on the way, right? The axioms you know from a tree decomposition. And every edge that we accommodate must live in one of these parts, so we're not allowed to add an edge like this. Yeah, and that's it. And now I've deleted one of these bags, but I've just chosen an arbitrary one at this time. And yeah, so it doesn't really matter which one you choose. There is a notion of cyclic decompositions now that wasn't available at the time. So Robertson and Seymour used this path decomposition that existed as a special case of tree decompositions. But notice that intuitively, if you have all these bags of size less than k, then if you delete any one of them, you can ask that the rest should form a path decomposition where you put all these vertices that belong to the bag that you have disregarded, you put them in every bag, right? So even if you have something like a cyclic decomposition intuitively, which we haven't made precise, you can imagine that you do get a path decomposition of size less than 2k if you pick any one bag and add it to all the others. So the definition of a vortex is there exists a path decomposition, such that for every bag, there is a unique vertex in that bag on the boundary of this hole, of this disk. And these vertices in the bags their linear ordering in one of the two cyclic orderings induced by the circle that bounds this disk. This linear ordering corresponds or is the same as the linear order of the nodes in the tree decomposition whose tree is this path. So that's a way of making it formal. You can read it up in the book where I've made the definition explicit. Okay, so all these vertices, other than the one that is special for each bag, do not live in the surface. Okay, so this entire graph, decomposed linearly as we see it here, meets the surface in only those pegs. Right, so that's a vortex. And the vortex has depth less than k if the width of this tree decomposition, whose tree is this path, is less than k. Questions about the notion of near embeddability, or indeed about the structure theorem? Okay. One little observation, remember the torsos are complete. The adhesion sets in the torsos have been made complete. And that implies that they can't be so big, because a complete graph that k nearly fits into such a punctured surface can't be unboundedly large. So in the surface itself, you don't have a kn by definition of the surface, right? That's how S was chosen. a separate S possibly for every torso, but every such S has the property that Kn doesn't fit in it. So there's no Kn in here, and every complete graph meets at most one torso, because a vertex in here cannot be adjacent to a vertex in another vortex, meets every vortex, at most one vortex. So a vertex inside a vortex, not in the surface, cannot be adjacent to a vertex in another vortex, simply because their edges are added from the inside of this to the inside of that. So our complete graph that supposedly resides in this surface plus vortices has fewer than n vertices in here, meets at most one vortex, and in this vortex it has at most k vertices, right? Same proof as we had for tree decompositions that a Kn must lie in one bag. So since we're allowed to delete up to k vertices at the start, that leaves us with a bound on the size of a complete graph that can live in such a thing at 2k plus n, right? K for the apex vertices, another k for the size of at most one bag in at most one vortex, and n, or in fact n minus 1 for the surface, right? So I'm not requiring this bounded adhesion here, but it follows. So every tree decomposition like that must have adhesion at most, or in fact less than 2k minus 2k plus n, and that will be important later. Right, there's a converse, but only a qualitative converse. So a graph that has such a tree decomposition whose torsos k nearly embed in one of boundedly many surfaces, every such graph, not every such graph, such a graph can have a Kn minor. So as we just saw, Kn minus 1 fits in the surface, and then, you can sort of, branch sets can leak into this structure here and link up. So you can expand your Kn minor a little bit if this K is big enough. So Kn minors can live in such structures, but not arbitrarily large complete minors. So for every such n, there exists an M such that these graphs cannot accommodate a Km minor. Right, and the proof is similar to what we just showed, that there's no Kn, there's no 2k plus n complete subgraph. And for minors, it's a little harder, but not much. Yeah, so bounded adhesion follows. And so this looks quite terrifying. Complicated structure, why all this complication? Couldn't they do it any better? No, they couldn't do it any better, at least not locally better. What do I mean by that? What I mean is that there are 4 ingredients to relax embeddability. 4 ingredients to this structure. One is apex vertices, another is these vortices of bounded depth, where you can put some stuff in but not too much. Another is allowing graphs embedded in some surfaces, not necessarily the plane, some more complicated surfaces, but not too large surfaces. That's the third ingredient, and tree structure, that the whole graph decomposes so that only the torsos have to fit in these surfaces nearly, That's the fourth ingredient. So once more, 4 ingredients: tree structure, embeddability in some surface, possibly complicated surface, but not too complicated. Embeddability, being allowed to delete up to k vertices, and being allowed to do some messy little bits in these vortices. These are 4 ingredients that somehow relax the requirements that we normally have of embeddability in, say, the plane. And I want to show you that all these 4 things are really needed and unnatural. So how do I do that? I'll show you for each of these ingredients a graph that doesn't contain Kn as a minor, but uses this particular ingredient so excessively that the other 3 ingredients are not good enough to accommodate, to allow for accommodating this graph without the ingredient we're looking at. So for example, first ingredient is tree structure. I'll show you some graphs. Unboundedly large graphs, which heavily use this ingredient of tree structure, and as a consequence, couldn't be accommodated without the ingredient of tree structure, even though they don't have Kn minors. So let me make it precise. So we need tree structure. So, by the way, these arguments or these examples that the 4 ingredients are really necessary are an exercise in the book, so they're not in the text. If you want to copy the examples, I'm not going to give you rigorous proofs that what I'm going to say that these examples really fit what I claim, but I'll give you the examples, and the proofs are not easy, not difficult once you have seen the examples. Okay, so note them down if you like. Tree structure. Take a graph with a tree decomposition into K5s and a very large binary decomposition tree, as large as you like. Right, so for every ingredient, I'm going to give you a class of graphs because I need to make them arbitrarily large. Because now I want to show that allowing only the other ingredients, even with bounds not equal to k, but any bound you choose, but some bound, will not be able to fit all these graphs into that structure if this tree, this binary tree T2, is chosen high enough. So grant yourself a bigger k, use only the other ingredients, and see whether you can fit this in. And I'll claim, no, you can't, as soon as I make the tree big enough. And why is that? So roughly, what one needs a theorem there, and that is that trees, in particular just the binary trees, have unbounded path width. That's a non-trivial theorem, right? So if you take path decompositions of these binary trees, tree decompositions whose decomposition trees are paths, then there is no bound on the width of these decompositions that you will need in order to accommodate just those trees, right? It's a bit, trees, even just binary trees, are very unlike paths, so that you can't make them flat. They just want to grow everywhere. It's a bit like a grid theorem, right? The grids don't fit into bounded with tree decompositions, because grids are sort of like flat, they're not tree-like. And in the same way, trees, binary trees that keep branching, are not path-like. So it's maybe not a surprise, but it does need proof that binary trees have unbounded path width. So in one of these vortices of bounded width, right, linear decomposition, path decomposition of bounded width, you can only fit an insignificant part of even a tree, let alone a fattened tree with bags that are K5s. So if you have one vortex, only a little bit of this tree will fit in there, right? You can find the blue tree also in white. And if you have K vortices, still only a little bit will fit into those K vortices, even if you could use more than one, if you let the whole thing grow arbitrarily high. So in each vortex, and there are only boundedly many, only an insignificant part of this graph will fit. And in the surface itself, also only an insignificant part will fit, because there are lots of disjoint K5s here. And there is something called genus additivity, which means that the genus of a graph, which is the lowest genus of a surface. When I say genus, I mean Euler genus, the lowest genus of a surface that accommodates this graph. This is additive. So if you have two graphs, one of genus A and one of genus B, then the disjoint union needs a surface of genus A plus B to have this accommodated. All this, by the way, is in the book in an appendix on surfaces. Only that. So that's bedtime reading. It's easy, I think quite intuitive. You sort of take your scissors and cut up some surfaces and so on, but it's rigorous. So it's easy, simple, and exactly what we need here. So I won't dwell on that in this lecture. Right, so that's it. Right, so you can delete up to K vertices. That doesn't affect this if you make the tree big enough. You can fit a little bit into vortices, boundedly many, only small depth. That affects only a bounded little bit of this structure. And in the surface itself, you can embed only boundedly many K5s. So these things don't fit in a surface with boundedly many vortices of bounded depth, even after deleting boundedly many vertices. All right, so that's why tree structure is really needed. So that's tree structure. Apex vertices. Why do we have to allow ourselves to delete up to K vertices? Well, same strategy as here. Let's make a graph that really needs an apex vertex. And that is you take a large grid, and then you add all the diagonals, right? So in every square you add the diagonals. So grid, large grid plus diagonals. Not both diagonals, no crosses, just add one diagonal, always the same, from bottom left to top right. That's still planar, right? And then, on top of that, we add one vertex adjacent to all down here. Okay, so that is something with something that looks very much like an apex vertex. It doesn't matter whether I take 1 or k minus 1 or whatever. So let's see that this graph doesn't embed or doesn't nearly embed or doesn't fit this structure theorem if we disallow the deletion of apex vertices. Yet, it doesn't have a kn minor, right? So this is planar. This doesn't even have a k5 minor, so with this vertex at the top, the whole thing doesn't even have a k6 minor. So let me show you that if we disallow this little bit of freedom here, if we disallow the deletion of up to k vertices, for example, of this one vertex here, then this graph doesn't fit into the structure. And the idea is, well, the same. Tree structure, remember we have bounded adhesion, right? And that's important here. If we have a tree decomposition of bounded adhesion, then only insignificant little bits of this big grid, will lie outside one central bag that must contain the entire grid, or torso in this case. Right? There will exist a torso that contains 90% of this grid. And it then must also contain this vertex. If it didn't lie in that torso, it couldn't be adjacent to everything in that torso. So all this would lie in one torso of this tree decomposition. And there we're allowed to put some vertices in vortices, but then the same applies. It doesn't help because a vortex has this path decomposition of bounded width, and grids cannot be decomposed in a tree-like, let alone path-like way, bounded way in this sense. So every such vortex would also have one bag in which most of this lies, and that cannot happen. And if you do it k times, it doesn't change. By the way, having k vortices and having one vortex is pretty much the same thing. So if we had k vortices, all of bounded width, depth, we could sort of dig little tunnels or build bridges in the surface from one and line them all up and combine all these vortices into one big vortex. That's just for convenience that we're allowing more than one vortex. Right, so apex vertices, the deletion of apex vertices is needed. What's next? Vortices. Well, okay, same idea. Take a graph that really looks like a vortex, big vortex, and then show that the other ingredients don't help. So what's a big vortex? Take a very large grid, and then around the perimeter of that grid, add edges that always just jump one position, right? Add vertices, add edges between, join vertices of distance 2 along the perimeter. And we do that all the way round. So this is really, this is the surface part, and then the outside is a hole with this as a vortex. Right, you see, you have a path decomposition here that contains all the yellow edges. So that's a nice example of a big, big vortex. And similarly, as before, we cannot accommodate that in this structure if we disallow vortices. And why is that? Well, if you delete up to k vertices, that doesn't change this. Right? If you try to put this in a tree decomposition of bounded adhesion, once more, by bounded adhesion, we can cut this grid only in very unbalanced ways. We can cut a little bit out, but we can't cut it in half by bounded adhesion sets. So there will exist a part or one torso in this tree decomposition that contains 90% of this. We'll log everything. And so that's it. No, and right. And we also need, I forgot to show you that here, we also need surfaces up to what embeddability of Kn allows. So we only want surfaces that Kn doesn't embed in, but the ingredient says that we must be able to use surfaces up to there, but that doesn't help here. Why is that? Because you can make lots of local little K5s, K5 minors. So if you look a little bit and fiddle a little bit on a piece of paper, you will see that there's a K5 minor here. Right? You can take 5, 1, 2, 3, 4, 5, and then you can find paths between these to make a K5 minor. So you have lots of those disjoint from each other, and they don't fit in any surface of bounded genus if there's too many of them. Right, so I gave you that argument here. That tree-like, if we don't allow tree-like structure, then these graphs, they don't fit in surfaces of bounded genus because there are too many K5s. I told you that there. I haven't done it here, so let me give you this argument here. Why can't we fit this in some surface? And the answer is interesting. It's a nice little argument. This is nearly a maximally planar graph. So all these faces are triangles. So this has nearly 3n minus 6 edges, or average degree nearly 6. Now, any graph, all graphs embedded in some fixed surface have an average degree of 6 plus little o(n), where n is the size of the graph. So that's an easy fact. It follows from Euler's formula. But that means that large enough graphs of this type will not fit in any given surface, because this has average degree, what? 6 inside here, plus 1 edge to the top. So this has average degree as close to 7 as we like. Right? But give yourself a surface then all graphs, all large enough graphs in that surface have average degree less than 6.5. Right, so these things don't fit in any other surface. Okay, and here the same is true because you have all these disjoint K5s. And that leaves me with one more ingredient. And, well, let me put it here. That we're allowed to use large surfaces as long as they don't embed Kn. The point now is that we need all of them. So suppose there's a surface that doesn't accommodate Kn. That's a cross cap. You've seen a cross cap before? So you cut a hole in your surface, and then you identify opposite points. So there's a hole in here, and then these are not edges. You identify opposite points. Right? And then you can prove that this is still locally homeomorphic to the plane, to the Euclidean plane. So after doing that, you still have a surface, and a surface with such a thing are called non-orientable surface, because you can't orient them in some way I haven't told you. But anyway, all surfaces look like that. And now the point is that if you have a graph that uses some surface that Kn doesn't embed in really, really well, then we cannot fit it into this structure, say, when embeddability is replaced by embeddability in the plane, near embeddability after deleting apex vertices and allowing for tree structure. Why is that? Well, take your favorite surface S that Kn doesn't embed in, and now put a very, very fine grid on it. Right? So if the surface is a surface like this, then you can put a grid around it like that. Right, so this is still a surface, and put a very fine grid along it. And then, if you do that here with more handles than just one, and maybe a cross cap, you can still show that this graph then does not embed in any simpler surface. And also, you can't tree decompose it. Same thing, same reason as why you can't tree decompose a big grid. Having vortices doesn't help because, again, in path decompositions of bounded width, you cannot embed a large, even a large grid. And deleting finitely many vertices doesn't help either. Right. Okay, so that's all the ingredients. Are there questions? And each example somehow shows how this definition came to be? No? Okay. Then let's move on to the proof of the Graph Minor Theorem. Okay, so what did we have to prove? We had to prove that if we have an infinite sequence, G0, G1, G2, G3, and so on, then we can find a good pair, right? We can find a Gi and a later Gj such that Gi is a minor of Gj. So that's what we have to show for every infinite sequence of finite graphs. So without loss of generality, all these graphs, Gi, don't contain G0 as a minor, because if one of them did, we'd have our good pair. So we may assume that the Gi don't contain this. So they're in here. Yeah, but do we have a structure theorem for excluding an arbitrary graph? Well, yes, we do. Because if we choose n big enough, to contain G0 as a minor, for example, n is the number of vertices, the order of G0, then if we don't have a G0 minor, we don't have a Kn minor, because if we did, that would contain G0, right? So if we assume that the Gi are in this class, they are clearly going to be in that class for n big enough, for example, the order of G0. Yeah, but for these, we have a structure theorem. So use Kn, excluded Kn structure for G1, G2, and so on. Right, so the structure says that these graphs, these Gi, have tree decompositions whose torsos satisfy certain requirements. And like Kruskal's theorem, which somehow says that tree structure doesn't impede well-quasi-orderedness, sort of very, very roughly, one can show that it's enough to show that the torsos themselves are well-quasi-ordered. So the set of all torsos that occur in these tree decompositions coming from the structure theorem for the Gi. So we have to find a good pair of Gi's. Gi is a minor of Gj. And what I'm claiming is that it's enough to find a good pair of torsos. Whenever we have an infinite sequence of torsos, some from the same GIs, some from different GIs, and just any sequence of torsos, if we can always find a good pair there, that is, if the set of torsos is well quasi-ordered, then the tree structures you can make from them are also going to be well quasi-ordered. And the proof is much like the proof of Kruskal's theorem. And of course, it's important here once more that the adhesion of these tree decompositions is bounded. So we have these well-quasi-ordered ingredients, and we stick them together in tree-like ways, but only always along bounded sets. Then the graphs we can build in a tree-like way from these well-quasi-ordered torsos are themselves going to be well-quasi-ordered. Right, so these torsos live in these surfaces. Nearly. Not all in the same S. So what we have to do is now to prove that these torsos are well quasi-ordered. To prove this, consider a sequence of such torsos. All embedded, each of them embedded in one of boundedly many surfaces. Torsos from for the earlier GI. Then same thing. We can assume that H0 is not a minor of these HI. Right? But if it was, then we'd have our good pair. And then there's something else we can assume, and that is that all these are nearly in the same S, right? There are only boundedly many S that occur here as surfaces that accommodate these HI. Yeah, but since we have an infinite sequence, just for every surface, each of these 17 surfaces, look at those HI that nearly embed in that surface, and one of these sequences must be infinite, right? So by moving over to a suitable subsequence, we can assume that all the HI, all the HI are in fact nearly embedded in the same, this is an A, in the same S, right, as I sort of rashly indicated there. Now, the nearly, of course, always is a K nearly. And I omitted that K because the K is going to change a little bit. Officially, we are given our K by the structure theorem, and but we're going to increase it a bounded number of times. But that's fine, because it's only boundedly often, but I'm going to omit reference to K here so as not to have to tell you each time which K I mean. All right? Okay, and so we have to prove that these torsos are now only those in the subsequence that all nearly fit in the same surface and don't have H0 as the minor, are well quasi-ordered, and we prove this by induction on the genus of S. This surface. And now we can use structure that this assumption imposes on the HI. And this is structure that has to do with S, because H0 is also nearly embedded in the same S. So we're looking now for a structure theorem about graphs nearly embedded in a surface in which do not contain some other graph that is also nearly embedded in that surface. And that shows that we don't really need that surface. So like in the grid theorem, if we look at graphs that are vastly planar and need a lot of plane, then they will contain every planar graph as a minor. So if we look at really, really big grids, they contain every planar graph as a minor. But as soon as we forbid some planar graph as a minor, the graphs that remain may still be planar, but they're not going to use the plane really. They're going to have bounded tree width. And we're doing the same for arbitrary surfaces here. We show that these HI here are well quasi-ordered by induction on the genus of this S. And there happens to be a theorem that helps us with that. We're assuming about our surface that some graph H0, which nearly embeds in it, is not a minor of an arbitrary graph that we're now looking at. Right? So we're now looking at an arbitrary HI that is nearly embedded in this S, and we're assuming about S that some graph H0, which is also nearly embedded in S, is not a minor of HI, just as we have it here. Then the assertion is that we can find a closed curve along which we can cut S to turn it into one or two simpler surfaces, which meets this HI only in a bounded number of points, L, where the bound depends only on S and on the graph H0 that we've forbidden as a minor. So here once more is our arbitrary surface, and let me show you now what such cutting curves might be. So here's a closed curve which cuts the surface into two simpler surfaces. Well, after cutting along here, it falls into two bits, but each of them has a hole, and we have to put a disk on that hole. That's what I'm calling a cap. Right? If we cut along here, we get two components, and we have to cap each of them. If we only cut here, then this will sort of open up, and we'll also have two holes, but there's only going to be one component. So we're going to have one simpler surface once we have capped those two holes. And similarly, for a non-orientable surface, so that's a bit more difficult to imagine. So here's the projective plane. Let me arm myself with lots of colored chalk. That's an egg, that's not a circle. That's a little better. So take a disk and identify opposite points. Okay, so all these points of matching color are the same point. And what you get is another surface, and that's called the projective plane. And now here's a circle, C, right? You travel along this disk on a topological path from this point of the disk, boundary point of the disk, to that boundary point, but which have been identified. So this is, in fact, a circle. And once you cut along there, can you see what you get? So it looks like you're getting two half disks, but these are still identified. So this is still the same point as that, and this is still the same point as that, and so on. So once you've cut along here, this still hangs on there like that. So what one really gets is, so when you take this half here and put it, identify it along here, what you get another disk. So these half things make one big disk bounded by that. So you get this, and here you have these points. Okay. So that is it's called surgery. So you cut the surface open, and maybe you put a plaster on to make it look like a surface again. Okay. Right, and now, what does the theorem say? The theorem says that we can find such a curve that hits the HI only in a bounded number of points. Now, why should that be the case? Right, so you could, HI has to be embedded in the surface, or nearly even only, but why can't HI be sort of a very fine grid-like thing like this? So could this be HI? No. If it's too fine, if this grid is too fine, then this HI will have H0 as a minor, because H0 also lives on this surface. And that's like the proof that I showed you about grids having any given planar graph as a minor. Start with your planar graph and take a very, very fine grid, and then you can find that embedded graph in this grid. And it's the same thing here. Since H0 is somewhere in this surface, if HI couldn't be cut in a way that hits it only boundedly, then it would be so fine everywhere that it would in fact contain H0 as a minor. Right, so those two things conspire to give us such a closed curve C along which we can cut S into two simpler surfaces, and that they are indeed simpler surfaces, have lower Euler genus. That is very simple to calculate and is also in the appendix on surfaces. Okay, so let's now use that surface grid theorem for the HI that we want to show to be well quasi-ordered. Right, so HI lies in there. Let me make it green perhaps so that you can see it better. Unless this looks white to you. Can you see that this white is green? Yeah, just a little bit. Okay, so that's sitting somewhere in this surface. Like this. The pointers that see the blue curve that cuts the surface into two simpler surfaces meets it in only a bounded number of points and will log these points are vertices. Right, now let's decompose hi into hi prime and hi double prime, the two sides on the left and on the right. So these are now nearly embedded in these simpler surfaces. So this is the surface S, and these two surfaces into which S is cut by cutting along C are called S prime and S double prime, or maybe it's only one. When we cut along here, we only got one surface, call that S prime. Then each of them, or in the case of having only one, the entire hi, fits into the corresponding simpler surface. And it does so nearly. And now let me write k plus L nearly. Right, I'm jacking up this k by the bounded number L that is bound of the number of points here. But since we can do this cutting operation of the surgery only boundedly often, because we're starting with a surface S of bounded genus, we'll change this k only boundedly often, so that will be fine. We can just replace the k by k plus the sum of all the L's that we ever use. Okay, so now we can apply induction and show that these and those are well quasi-ordered. And all the hi prime that we get and all the hi double prime that we get from the hi's, I is running along these indices here with these two assumptions. We can assume that the set of all these hi, prime or double prime, is all the primes are well quasi-ordered and all the hi double prime are well quasi-ordered. And then also the pairs are well quasi-ordered. This looks like Higmann's lemma. Remember that when X is a well quasi-ordered set, then the set of finite subsets of X is also well quasi-ordered, but it's a lot simpler. I mean, it's not for subsets, but it's for ordered pairs, but it's easy. So if we have an infinite sequence of these pairs, we can find an infinite subsequence that is increasing in the first component, and in that subsequence, we can find a good pair in the second component, and then we'll have found two pairs where this is a minor of the other first, and this is a minor of the other second. So for pairs, it's really easy. But we need this with roots so if we have such a good pair of pairs, right, hi prime, hi double prime, and hj prime, hj double prime, where the first prime is a minor of the first prime, and the second prime, the double prime is a minor of the double prime, then we can't fit them together as we want to from the assumption that this pair is less than that pair, pairwise minors, to the assertion that we really want, namely that hi is a minor of hj. And the reason we can't do that naively is that we need to fit them together here. So if this is a minor of some hj prime, where this gets lost somewhere up there, and this is a minor of some hj double prime, where this is lost somewhere up there, then from the fact that these halves embed in the corresponding half, we can't deduce that the hi as a whole, with these halves pasted together, embeds in the hj as a whole, because there we would have to fit the two halves, hj prime and hj double prime, together in the same way. But you can keep track of these boundedly many roots and write that into the requirement of your minor relation for the left and for the right, so that these minors respect are constant on these roots. Okay, and now we're nearly done. Or are we done? Right, I've completed the induction step. And that seems to be it. There's something crucial missing. That's the induction start. Right, remember, for every surface that is not the sphere, can we find such a cutting curve? Of course, we can't cut the sphere into two simpler surfaces because there aren't any simpler surfaces. Right, all this doesn't work. This induction doesn't work without a start, and the start is that for the sphere, S2, we have to prove the well-quasi-orderedness of these hi without the help of that. But what does it say? It says that all the hi that are planar, embeddable in the sphere, are well-quasi-ordered as long as there exists some other planar graph, H0, that is not their minor, for none of them. And that's true, because if you exclude a planar minor, then all your graphs, planar or not, have bounded tree width. And the graphs of bounded tree width, as we saw earlier, are well-quasi-ordered. So that's the induction start. And then the whole big edifice is erected on that. That's the end of the sketch of the Graph Minor Theorem proof. As it could have been, as I said before, it is in fact quite a bit different from this, but technically much, much more complicated still. But still, so here you have an overview of what might be a proof.